the you know the symmetric pairs are conjugate to each other. If that's the case, then this matrix is Hermitian. Okay? So you can see that this is a Hermitian matrix. I can give a much larger example for Hermitian matrix, but basically it satisfies these two rules. First, the diagonal elements are all real. Okay. Second, the conjugate, the symmetric pairs are conjugate to each other. Okay. I mean, the diagonal must be real. If it's not real, think about that. I mean, because I mean, MH, you are going to do the conjugate and then transpose. But if it's for diagonal element, I mean, the transpose, doesn't change the position, right? So, I mean, if an element after it becomes a conjugate, it equal to itself, the only possibility is it is real number, right? So that's why the diagonal element must be real. Okay. As for like the symmetric pair must be conjugate to each other. That's obvious. And then, okay, once we have this definition, there are some interesting results. Okay, the eigenvalues of Hermitian matrices are all real. Further, eigenvectors belonging to distinct eigenvalues are orthogonal. First part. If let's say we have eigenvalue, we have a matrix A, and we have an eigenvalue, okay, lambda. So now AX equal to lambda X, right? And now we need to show that that lambda must be real, right? Right? Okay. So and we know that the fact that A equal to A H, right? Right? I mean, A is Hermitian, right? Okay. So, if you put like a Hermitian on both sides, okay, because A lambda, AX equal to lambda X. So if you put Hermitian on both sides, or h a x the x h times a times x. Okay, so we need to construct this thing. Okay. A is a Hermitian matrix. Lambda is eigenvalue of A. X is eigenvector. Okay, we don't do lambda. Then alpha be x h a h x. Okay. So that's got like this part. So alpha must be real. Okay, because alpha bar is going to be alpha Hermitian, and then you put the Hermitian on this thing. It's, you are going to reverse the order and put the Hermitian. So it's going to be x Hermitian, x Hermitian and a Hermitian, and x Hermitian. So it's going to be x Hermitian, a Hermitian. Well, a Hermitian is a because we know a is Hermitian already. So x Hermitian is x. So it's going to be the same as this one. So this one we know, according to our definition, is alpha. So alpha bar equal to alpha. So alpha must be real, right? So since alpha equal to x h a x, okay, equal to x h lambda x, because ax equal to lambda x, right? Here x is our eigenvector. X is our x is eigenvector. Lambda is the corresponding eigenvalue. Okay, so we can get the lambda in front. So it's going to be x h lambda x. So that's like an x squared. And we know x squared, this one, must be greater or equal to 0. It must be real. You represent the length of x. Okay? So in other words, lambda is alpha divided by the length, the square of the length of x. So it must be real. So the key idea is to construct this x h a x first. Okay? So far so good, right? Okay. So we here, okay, up to here, we know like lambda. So any eigenvalue must be real. Okay. And then we need to argue that, if there are two eigenvectors for Hermitian matrix, then these two eigenvectors must be orthogonal. In other words, their inner product must be 0. Okay. So that x1, x2 in eigenvectors belong to distinct eigenvalues, lambda 1 and lambda 2. Okay. So we consider the ax1 Hermitian x2. Okay, ax1 Hermitian x2. So it's going to be, if you apply Hermitian in here, so it's going to be x1 h ah, okay, x2. So this one, okay, ah equal to a because we know a is a Hermitian matrix. So this one will be x1 h a x2. So a x2 we already can get like lambda 2 x2. So we have lambda this thing equal to lambda 2 x1 h x2. So another, okay, ax1 h x2. Okay, another way to deal with this is we make this thing, okay, we try to get like h, okay, out. Okay, this thing equal to this one. Why? Because if you apply to here, okay, the x2, x1 will go to the front, x1 h, and then ah, okay, this one, okay, and x2 HH, which is x2, okay. So this one equal to this one, and this one, okay, according to, our definition, ax1 is lambda 1 x1, so we can put lambda 1 here. So x2 h x1 h. So again, remember previously we already showed all the eigenvalues are real, right? All the eigenvalues are real. So you can get this real number out, okay, from this h, because you don't need to do a conjugate. The conjugate of real number is still the same, right? It doesn't change. So you just get like lambda 1 out here. And this one, h is going to be x1 h, x2 h h. So it's x1 h h x2. So you can see the same thing. This one, if you try to handle it differently, one give you lambda 2 x1 h x2. One give you lambda 1 x1 h x2, because x1 h x2, this part are the same, right? The different parts, lambda 2 and lambda 1. And remember, okay, this lambda 1 and lambda 2 are different. So the only possible explanation is that x1 h x2 is 0. Okay? The only possible explanation is x1 h x2 is 0, which means x1 and x2, these two eigenvectors from different eigenvalues, they are orthogonal. Okay? So this is like very interesting proof, but you need to, how should I say, know exactly how to construct it. Okay, that's like something you need to know how to do, okay, in order to give your formal proof. Okay. And then, okay, unitary. I think we, as I said, I have a meeting which is far away from here, so I don't think I have time to finish the discussion unitary part. Okay, so I'll stop here. Okay, and I'm going to give some practice questions today. Okay, tonight. Okay, including some part in this section, but not the unitary and the Shor's theorem and the spectral theorem. This stuff, I will not talk about that. I will not include that in the practice questions. Okay, but yeah, some part of this section will be included in the quiz. Okay, so yeah, that's it. Okay, so keep in mind, check out practice questions tonight. Okay.